Hi everyone, welcome back. This is Sachin Kumar, pursuing PhD from the Department of Material Science and Engineering, IIT Kanpur, working under the supervision of Dr. Kaustubh Kulkarni, and my research topic is diffusion in studying the diffusion in nickel-based ternary alloy. Okay, so today's topic is about. So we know that by the diffusion process there is a reduction in the Gibbs energy. So after diffusion will take place due to diffusion is take place to reduce Gibbs free energy, right? Okay, so what is the driving force to reduce this Gibbs free energy? So what made to reduce its Gibbs free energy, we will see in today's class. Okay, so first of all we will see we are studying the diffusion consisting of B rich side consisting of two atoms A and B atoms. So this is B rich side and this is A rich side, and we are mentioning 1 and 2 so that we can mention in the Gibbs free energy, composition versus Gibbs free energy diagram. This is the free energy of a 2 and this is a Gibbs free energy of 1, G1 and G2. When we are just joined, then the average Gibbs free energy will becomes G3. So it needs to reduce its Gibbs free energy from G3 to G4, correct? This is a G4 value. So this will take place by moving an atom from moving an atom B from towards A rich region and A towards B rich region. That means there is a movement of the atom towards the Gibbs free energy will reduces only when there is a movement of atoms towards the down the concentration gradient. There is a lower from higher concentration gradient to lower concentration gradient. That means down the concentration gradient. In this case, we will have down the concentration gradient. Right? So this is not the case. So everywhere in each and every cases, the Gibbs free energy will reduces only in the down the concentration gradient. Because of this one, I have taken the one more example of miscibility gap. When there is an miscibility gap, the Gibbs free energy phase diagram, Gibbs free energy diagram will show the negative curvature. This is the negative curvature which it is showing, and this is a G2 value, and this is G1 value, and the average Gibbs free energy is G3. Right? It needs to reduce from G3 to G4 as in the case of this one. But here it's different. Here the diffusion of an atom will take place from from lower concentration to the higher concentration gradient. That means this is the A rich region and this is the B rich region. The atoms will move towards the B rich region, and here the A rich region, the A atoms will move towards the A rich region. So hence we can say this as the diffusion will take place up the concentration gradient. Correct? So this is the case. That's why we can't say the concentration gradient. So in case 1, we see the diffusion will take place down the concentration gradient, whereas in the case 2, the diffusion will take place up the concentration gradient, right? But we can't say the concentration gradient is only the parameters is a driving force for the diffusion, because in both the cases it's totally different, correct? But one more parameter is there, that is called chemical potential. So chemical potential is a parameter where you can define the driving force for the diffusion from higher. The diffusion will take place from higher chemical potential to the lower chemical potential in the both the cases, right? So I will demonstrate with an example. So we know that the chemical potentials are drawn or obtained by drawing a tangent to the at the particular point in the Gibbs free energy diagrams. So I have drawn the tangents, and this is chemical potential of atom A into second component, at atom A in a first component, and these two difference will give rise to the driving force. This is for higher to lower. Similarly, so this is the chemical potential of atom A in case 1. That's why this is also from higher to lower, correct? So that's why the driving force for the chemical potential, driving force for the diffusion is from higher chemical potential to the lower chemical potential. So, I will write it this one. Driving force for diffusion is from higher chemical potential to lower chemical potential. So this is the common. It's applicable for the both the things. This is theoretical one. Okay, we got obtain the conceptual driving force. From the derivation also we can say chemical potential is a driving force. I will explain that one also by drawing by with the help of derivation. Okay, so fundamental equation from the previous slide we got for the chemical potential related to the activity of the system is given as, I will write relationship between chemical potential and activity is given by mu I equal to mu I naught plus RT ln AI. We know that AI equal to gamma into xi, right? By differentiating with respect to x on both sides, this will be the 0 because it is a constant term. RT ln, I'll add differentiation here, AI, then RT d of ln xi to dx plus d ln of mu I divided by dx. So this is a thing, right? Here this is a coefficient constant, hence differentiation of a constant will leads to the 0, correct? Then by differentiating this one, we will obtain as xi dxi divided by dx. So here is the equation to write to convert the potential gradient, chemical potential gradient to the concentration gradient. We know that this is for diffusion is driven by chemical potential gradient, not by the concentration gradient. Why we need to consider this one? This is the easily measurable quantity. That's why we are considering the concentration gradient as a measurable quantity for the diffusion. This is the thing. Okay, this is a deriving the concept. By derivation, we got the relationship between the concentration gradient versus chemical potential gradient. We come to know the driving force for the diffusion. Now we are getting into some terms used in the diffusion in solids, that is diffusion flux and the frame of reference. We will start with the definition of the diffusion flux. Diffusion flux across the plane is defined as the amount of a component crossing per unit cross sections of a plane per unit time is called diffusion flux. So for your reference, I will write this one. Defined as amount of the component crossing per unit area, unit cross section of plane per unit time. I think most of you heard about the electric fluxes, magnetic flux, everything. Similarly, it is having diffusion flux is defined. This is the amount of the component crossing per unit area, 1 unit area of cross section per unit time is called flux of that component I. Here I'm for your time being I'm explaining. Here 3 arrows are there, and in another component, so it is J. It's having only 2 arrows, and here we can say the flux of I is greater than the flux of J. Right? This is the meaning of this flux. Then the unit of J can be written as, it is denoted with the help of term J, and it J of I is equals to amount of I to meter square per second. So there is different various units are there, that is mole per meter square per second, or atom per meter square per second, or kg per meter square per second, or meter cube per meter square per second. This is can be written as meter per second. This is the various units of a flux. Then we are knowing, so what is the physical significance of this diffusion flux? I will take a whiteboard for this one. Physical signification of flux. Okay, so for this one I am considering the one plane P, and this is the profile of concentration, which is this frame of reference, composition wavefront of width dx, and this is dx by 2, and the unit, this is unit area of cross section. It is having unit area of cross section, and we are having the laboratory fixed frame of reference outside the this is laboratory frame of reference. Okay, consider that the Ci amount of component will pass us through the distance dx, and the frame of reference is placed at the distance of dx by 2 as shown in this figure. So this is Ci amount of component is passing. Then if we consider that Ni number of an atom is in a small volume around the frame of reference, then the concentration of the ith component is given by, the concentration is given by Ci is equals to Ni to A by dx. We know that the concentration is the number of atom passing per unit volume. This is a concentration. A is the area of cross section and dx is the length of this one. Right? This is a concentration. Now we can determine the flux by considering the laboratory frame of reference. This is a laboratory frame of reference. Frame of reference. Then from the definition we can write J tilde of I component is given by Ni to the number of atom passing per unit area per unit time, and then we can also write it this in the form of Ni to A into dx. So dx by t, I multiply divide the dx term. Then we can write this as Ci and this as velocity, distance divided by time taken, from this equation 1. Then the Ji tilde equal to the Ci into Ui. That means flux is equals to flux of I is equals to concentration of I into the mean velocity of the I component. This is the physical significance. For example, for time being, this is the frame of reference is constant. For our consideration, we are saying this frame of reference is moving with a velocity of psi. Velocity of the plane P. Plane P, then this above equation, this equation 2 will become Ji tilde equal to Ci into Ui minus psi value. Correct? Then this is given as not tilde value. Here I will remove this tilde. This will be making confusion. Dash I will mention as J dash. Then multiplying we get as Ci into Ui minus Ci into phi Ji dash. That means Ji dash is given as Ji tilde minus Ci into phi. This is a final equation when there is a frame of reference is moving. For moving frame of reference, reference. This is the all about the fluxes and the physical significance of the diffusion flux. This is a very important equation used in everywhere. Physical significance, that is the flux of I is equals to Ci into mean velocity, the concentration into mean velocity. Okay. Now we have completed this diffusion flux and the physical significance of diffusion. In next video, I will brief about this frame of reference. What is frame of reference? There are three kind of frame of reference, that is volume fixed frame of reference, mass fixed frame of reference, and mole fixed frame of reference. Correct? Thank you.